So, new topic, kind of just a fun topic. It's not really, there's not a lot of math involved in this. It's more of a visual representation. Slope fields. So, slope fields are useful for a couple reasons. At times, we may be incapable of solving differential equations. There may not be integrals, right? It may not be a closed function where we end up being able to take an antiderivative. But you can always get a visual appreciation for what the solution to the differential equation looks like, even if you can't solve it, right, using slope fields. So what are slope fields? Well, slope fields, they're really, all they are, it's just a visual field where we're going to draw little, and this will be familiar because I've done this all year. We're just going to draw little tangent lines in that represent the values of the slope, the derivative, at ordered pairs at points in the plane, right? So for example, like if we've got the differential equation dy dx equals y, okay, so that means our derivative in this case is a function of only y. So we can just pick ordered pairs and plug those in and calculate the values of the slope to build our slope field. Okay, for example, like if we picked, if we pick y to equal, what if y equals 1? What could x equal? Well, x could equal anything, because one thing you want to notice here, our derivative is not dependent on x, is it? Doesn't even show up in there, right? So whatever x value we pick shouldn't have any impact on our answer. What is that going to tell us visually about our slope field, right? So if x could be, we're graphing from -10 to 10, so it could be anything from -10 to 10. It doesn't matter. What's the derivative going to be if y is 1? Going to be 1, right? Dy dx equals y, so it's 1. So if I go to the point, for example, 0, 1, I'm going to have a slope of 1. But the fact that it's the same, that the x value doesn't impact anything, means those are all just going to look like that, aren't they? Right? If I look at a horizontal slice through this field, the slopes are all the same, right? Because x doesn't have any impact. Only the y value impacts the slope of the function, right? What if I pick y equals 0? What's my output? 0. Good. So then if y equals 0, that's my slope field, right? See how that works? If I pick -1, it's -1. I don't want to do too many of these. Whoops. But you get the idea how we could do this, right? So now they're looking like they have slopes at all those points. Our little tangent lines have slopes of -1. Well, it just so happens that I built a little tool here to help you guys see this. Okay, so there's what the slope field would look like for this thing, right? So you notice that the rows, if you look across a row, the slopes are all constant, okay? And this gives us an idea of the slope field. So what does this mean? Well, it guides, it's sort of like saying, if have you ever seen like if you look at on the NOAA site and they want to show you like wind patterns and stuff. Have you ever looked at that one where they show you a little directional, like the wind is blowing over, looking down on the state of Oregon, there would be, it's blowing from the south to or from the southwest to the northeast in one place, and then it shifts, and you know what I mean? And so you kind of get a little picture that looks like that, with that all be little arrows showing which way the wind is blowing. Have you ever seen those? That's a good model of a slope field. Like if you were to drop, just like a feather into the air over Oregon, and you watched it, pretend it was really light, so it stayed in the air the whole time. Where would it go? Well, wouldn't it go, like if I drop it right there, it would just follow that trajectory, because that's the way the wind would push it, right? So if I want to draw individual trajectories through this, what are individual trajectories? Well, those correspond to solutions of the differential equation that meet some particular condition. They're going to go through a specific point on the graph, right? For example, we might say if I go back here for a second, like we might want to find the one. Does this ask for one? I don't know if it really out, but what if we wanted to find the one that goes through the point 0, 2? Okay, we could do that, right? We could just adjust the value of our constant, and now it's called k in here in my little program. But if I adjust the value of k, we can find the trajectory that goes through the point 2, 0. There it is, right? Everybody see that? Okay, so that's the trajectory. That would be the graph of the particular solution that meets the initial condition that when x is 0, y is 2. Isn't that cool? Right. So this is even built. I'll put this up on that little Google Doc where I've got Desmos stuff. But this is kind of cool. What I did is I just pirated something somebody else had done and just made some changes so it meets our needs. If you drag this thing along, it's kind of cool. You can, like this little point, as I drag it, it's going to change in response to what the vector field is, and it tells me what the slope is what the slope of the tangent is at all these points, and it gives you just a little. What it's reading out are the values of x and y, but the tilt of that thing is showing you the slope, right? Okay. Yes. I can drag k. You mean, can I grab this and drag it? Yeah. Yeah, so these are just, all this is saying, these are the different trajectories that correspond to different values of the constant we get, of the constant of integration that we get. Well, no, because when we integrate, right, we always get a plus c at the end. I called it k. I mean, I used k because the guy that had done this from some foreign country had called it k. And so I just didn't want to change everything, but I built it so I could do specific functions on here instead of just one. But anyway, so what's your question? It no, well, you're right. The slope doesn't change, but the trajectory does, right? Because this represents an infinite number of different trajectories. It's a family of curves. We want to pick the one that goes through our initial condition, right? Like that's not the one that goes through 0, 2, right? But this one is. What's that? If I graphed what now? No, it's not e to the x. Yeah. Does that make sense? I can, yeah. Yeah, I'll put this on I'll put it on there so you guys can play with this if you wanted to. It is kind of satisfying to just drag that little thing around. These are fun to work on. My wife would beg to differ. She thinks I've been a little too nerdy lately working on my calculus stuff, but I spent a little too much time on this. So there's some example of some individual trajectories, right? Now, what do we notice about these trajectories? So if you're trying to, like on the test, there are some questions that just ask you to kind of think in terms of trajectories. What are the general rules? Well, I mean, you're just going with the flow, right? You're just following these tangents. So it would be wrong to be cutting through tangent lines, right? You'd never be cutting through tangent lines. You'd always have to be kind of going with the tangent lines the whole time, right? Okay. But you can see some kind of cool stuff on this. If you just look at this slope field, you can see that, for example, look, I've got an asymptote right there, don't I? Because at y equals 0, I've got only 0 slopes. And so if I extend that out to the extremes, well, look, I've got an asymptote to the left then. The function's going to hug that as we go really far to the left, isn't it? It's never going to cross that, right? Okay. Okay. Moving on. So we could look at another. Oh, I guess maybe I didn't. There might have been one more thing at the bottom of this. Did I have? Oh, yeah. Okay. So, right. So you notice here, And I already alluded to this, but because the variable x does not appear in the derivative, dy dx is insensitive to x. It doesn't depend on x. And so if we look at horizontal rows of our slope field, the slopes stay the same because x is not a part of the derivative function. Okay. Compare that to this guy, right? dy dx equals x squared minus 2x minus 3. Now we could, I won't even bother plugging in a bunch of values. That just takes too long. But we could factor that, right? That's a trinomial that's factorable. And so if we factor that, aren't I just going to get x minus 3 times x plus 1, right? So what's that tell us? What are the x values where our derivative is equal to 0? 3 and negative 1. What do you notice about the variables in our derivative? Are there any y's? So what's that going to mean when I look at the slope field? What's that going to tell us? If there are no y's, vertical lines should be, the slope shouldn't change as I move vertically, right? Because y is not a function, is not a part of our derivative function. It's only a function of one variable. So if we look at this one, there, oh, it's on the wrong screen. Okay, this guy, notice what we see. I see one thing I should have changed on this, would have made it a little, I should have had the colors go the other way on this one, darn it. Next year. Look what we see here on our slope field at negative 1 and positive 1 and negative 3, right? Negative 1, positive 3, sorry. I get, look what happens. I get horizontal tangents. And notice that if I look vertically at any of those columns, the slopes don't change, right? So we could even do more than that, right? We could even look at this and say, okay, well then where should this be positive, right? Well, we would just be essentially graphing this function, right? If we graphed this function, this is an upward opening parabola with x-intercepts at 3 and negative 1. So it's going to be negative between 3 and negative 1 and positive everywhere else. Well, our slope field should reflect that. We should get negative slopes between the zeros and positive slopes outside of the zeros then, which we do. Look at that. Negative slopes between negative 1 and positive 3, and everywhere else I have positive slopes. Okay. Again, if I want to find the one trajectory through the point 0, 2, well, I've just got to vary the constant until we get that trajectory, and there it is, right? There's the point right there. There's the point 0, 2. So that would be the graph of the particular solution of that differential equation with that initial condition. Y is 2 when x is 0. Okay, isn't that cool? So I'm not even going to bother graphing it. I mean, you get the idea. Let's maybe see if we can squeak in one more here. Now this one's, finally we get one that has y's and x's, right? So rather than us plotting this thing, I'm just going to cheat and use the technology to give us a plot of this. Okay, so now here is, let's just focus on just the, slope field for a second. Okay, so I got to go maybe do that. Okay. Now, what do you notice here? Okay, like what could we do here? I've got this, the derivative is equal to x or y minus x. Okay, this is really a pretty sophisticated way to think about this, but you guys are ready for this. What if we wanted just to find, this time we involve both x's and y's. So notice that if I look at an individual column, yeah, the slopes are changing, right? Because as y changes, that impacts our derivative. the rows, same thing. Slopes are changing because x is a variable included in our derivative, right? Okay, but are there any places where I could see constant slopes? Like equilibrium, these are sort of equilibrium values, you'll call these eventually. Yeah, what if I just set this derivative equal to a constant and solve? For example, like what if I say I'm going to set it equal to 0, right? Well, okay, so if the derivative is equal to k and k is 0, then I just get y minus x equals 0. That's the same thing as y equals x, right? So look what happens then. If I look at the line y equals x, which is a line that goes, slope of 1 through the origin, what do you notice about all those slopes there? They're 0. Look at that. Isn't that cool? Oh, okay. We'll wrap this up, the last few problems tomorrow, and then I'm going to show you. I got this, and I've got to show you some really cool stuff, some volumes of revolution and volumes by slicing. So those are the last 2 sections we'll talk about, and then we're done. Okay. And I can get all that stuff in. I guarantee I can get all that stuff in the next 2 or 3 days.